Now we shall examine the meaning of point estimation of population parameters. Estimation of the population parameters like mean, variance, proportion, correlation, coefficient, etc. from the corresponding sample statistic is one of the very important problems of statistical inference. The estimation of the population parameters is imperative in making business decisions. For example, a manufacturer may be interested to estimate the future demand for his product in the market. The manufacturer of, let us say, bulbs or tubes may be interested in estimating the average life of these bulbs. A manufacturer of any such equipment may be interested in knowing the quality of the product by estimating the proportion of defective pieces in a particular lot and so on. These estimates can be obtained either by the census method or by the sample method. In the estimation of the parameters, we need to do testing of hypothesis based on the sampling distribution of a statistic and its standard error, which plays a very important role. Using a sample to draw conclusions or to infer about the population is called inferential statistics. Problems of statistical inference are of two types: problems of estimation and the testing of hypotheses. While problems of estimation derive a plausible value of the parameter of interest from alternative values, tests of hypotheses decide whether to accept or reject a specific value or a set of specific values. We discuss now about point estimation. The one or more characteristics of the population are called the population parameters. The population parameter is represented by the symbol theta. The aim of point estimation is to select a single number that is based on the sample data that represents a sensible value for theta. This value is called a point estimate of the population parameter theta and is represented by theta hat. The representation theta hat does not reveal the statistic used as a point estimate for theta. A point estimator refers to the statistics used while its value is the point estimate of the parameter of interest. For example, the population parameter of interest is the true average lifetime of batteries, let us say mu. We take a random sample of 3 batteries, n is equal to 3, and observe their lifetimes in terms of number of hours. This gives us 3 different readings, namely x1 which is 5, x2 which is 6.4 and x3 which is 5.9. The sample mean can be considered as a sensible possible value of mu, and hence it is called a point estimator of mu. The true average lifetime of batteries is its value, which is x bar, which is equal to 5.77 as obtained from the 3 estimates calculated from the sample. This is called the point estimate of mu, since a single point on the real axis is used to estimate the population parameter. The representation of the sample by theta hat, does not reveal the exact statistic used, or it does not specify that the sample mean has been used to approximate the true average lifetime of the batteries. The standard error of a point estimate is a measure of the precision of the point estimate. It is the standard deviation of the estimator theta hat represented as sigma theta hat. Standard error can be estimated and is called the estimated standard error in the case which involves unknown parameters whose values can be estimated from the sample. For example, if it is known that the population is normally distributed, then mu hat is equal to x bar is the known to be the best estimator for mu. It is best because it has the minimum variance and it is also an unbiased estimator. The standard error of mu is equal to sigma upon under root n, where sigma is the population standard deviation and n is the sample size. However, if the population standard deviation is unknown, that is, in the case where the unknown population parameter for the unknown population parameter, then the estimated standard error is used, which is equal to S upon under root n, where S is the estimated standard deviation from the sample. After studying this module, you shall be able to identify the need to know about properties of point estimators. You would know the basics of point estimation and standard error. You would know about the desirable properties of point estimators. Let us begin by understanding the properties of point estimators. A particular value of a statistic which is used to estimate a given parameter is known as a point estimate or an estimator of the parameter. A good estimator is one which is close to the true value of the population parameter in the underlying population. In point estimation, a sample statistic, a numerical value, is used to provide an estimate of the population parameter. A single population parameter of interest, that is theta, can be approximated by more than one reasonable, sensible, or plausible point estimator. For example, a plot of a sample of around 20 observations is generally normally distributed. Hence, it is assumed that the population distribution is normal with a mean equal to mu. Point estimators used for mu can be the sample mean or the sample median, since for a normal distribution mean is equal to median, hence the distribution is symmetric. Also, the measures average of two extreme values or 10% trimmed mean can be used. Each of these point estimators use a different measure to locate a center of the sample to approximate the underlying mean mu. Or, for example, the parameter of interest in the population is the population variance sigma squared. The point estimator can be used to estimate the population variance, which is the sample variance. The sample variance is sigma hat squared, which is equal to sigma bracket xi minus x bar bracket closed whole square divided by n minus 1. This discussion on existence of more than one point estimator of a population parameter brings forth the following question. Which of the estimators is closest to the population parameter value? One way to answer this question is by using the mean square error MSE. In statistics, the mean square error of an estimator measures the average of the squares of the errors, that is, the difference between the estimator and what is actually estimated. It is the expected value of the squared errors for all the samples. Squared errors will be small for those samples for which the estimator is close to the true parameter, while it will be large for those samples for which the estimator is far from the true parameter of interest. An all-inclusive measure is hence the expected value of these squared errors or the mean square error. An estimator with a smaller mean square error shall be a better estimator. The main problem with the use of MSE is that it depends upon the value of theta, giving smaller mean square error for some values of theta than for other values, since the exact value of theta is not known. Hence, we have to return to the question we had set out to answer, namely, which of the estimators is closest to the true population parameter value? The above question can be answered by using only those estimators which have a few desirable properties which we shall now discuss. The most important property is that an estimator should possess is unbiasedness. And once we have a set of unbiased estimators, we should look for one that has the minimum variance in the set of given unbiased estimators. Moving on to understand what is an unbiased estimator. An estimator is said to be unbiased if its sampling or probability distribution is centered at the true value of the population parameter. That is to say that the average value of the estimator in repeated sampling is equal to the true value of the population, the estimator, or more precisely, the expectation E of theta hat is equal to theta. An important point to be noted in this definition is that the expected value or the mean or average has to be equal to the true population parameter and not any other measure of the center like the median. This implies that the definition applies to both symmetric and skewed distributions. In the figure, the left side of the diagram shows symmetric distribution, whereas the right side of the diagram shows skewed distribution. In both the diagrams, the expected value is equal to the true value of the population parameter. Thus, unbiasedness is applicable in case of both symmetric and skewed distributions. Does this definition produce the same kind of difficulty as the mean square error criterion, namely its dependence on the knowledge of theta, and which in turn renders estimation useless since theta is already known? This, however, is not the case because the property of unbiasedness is derived from the general properties of the sampling distribution of the estimator and hence does not depend on the population parameter. The property of unbiasedness is derived for few estimators when X is a binomial random variable with the parameters n and p. The sample proportion p hat is equal to x by n, which is an unbiased estimator of p. This is proved as follows. The expectation of p hat is equal to the expectation of x by n, which is equal to 1 upon n, the expectation of x. Therefore, this is equal to 1 upon n into np, which is equal to p. Hence, the expectation of p hat is equal to p. Hence, for a binomial distribution, irrespective of the value of p, the sampling distribution of p hat is centered at the true value of p. The second property is when X has a uniform probability distribution from 0 to an unknown maximum value of theta, so that the parameter of interest here is the maximum value of theta. For example, X is a reaction time to a certain stimulus and has a uniform probability distribution. If we take the point estimator of theta to be equal to the maximum of x1, x2, x3 up to xn, where x1, x2, x3 up to xn is a normal random sample of the reaction times, it can be shown intuitively that expectation of theta hat is less than theta. Since the estimator will never overestimate, as the largest sample value cannot be larger than the largest population value by logic, and hence will in general underestimate theta. Precisely, it can be shown that expectation of theta 1 hat is equal to n upon n plus 1 into theta, which will be less than theta. Hence, this estimator has generally a tendency to get underestimated and hence creates a bias in the estimate. This estimator can be modified to get an unbiased estimator theta 2 by the following formula. Theta 2 hat is equal to n plus 1 upon n max of x1, x2, xn. Hence, the expectation of theta 2 hat is equal to E bracket n plus 1 upon n max bracket x1 x2 up to xn bracket closed. This is equal to n plus 1 upon n star into expectation of the max of x1 x2 up to xn. This is equal to n plus 1 upon n into n upon n plus 1 theta, which is nothing but theta. This implies that when we use theta 2 hat against theta 1 hat, there are going to some samples that overestimate theta, while other samples underestimate theta. But in the long run, there will not be any systematic underestimation or overestimation of theta. Moving on to the next property, we have, let us say, x1, x2, x3 up to xn be samples, random samples from a distribution with mean mu and variance sigma squared. Then the estimator is as follows. Sigma squared hat is equal to s squared is equal to sigma of xi minus x bar whole squared divided by n minus 1. This is an unbiased estimator of sigma squared. This is to specify that the estimator with n in the denominator, that is sigma of xi minus x bar whole squared divided by n, is a biased estimator. The last property we have is that if x1, x2, xn is a random sample from the distribution with mean mu, then is a unbiased estimator of mu. If the distribution is also continuous and symmetric, then median and any trimmed mean are also unbiased estimators of mu. The first proposition is a restatement of the rule of expected values, namely expectation of x bar is equal to mu for possible values of mu. The proof of other results are difficult to state. The last part of the properties point out to the fact that the principle of unbiasedness is not enough to select an estimator, since a large number of unbiased estimators exist for normal distribution population of the population mean. Hence, the principle of minimum variance must be used to choose amongst large number of unbiased estimators. The principle of minimum variance unbiased estimation MVUE states the following. Choose the estimator among all the estimators of theta that are unbiased, which has the minimum variance. The resulting estimator is called the minimum variance unbiased estimator MVUE of theta. In other words, if we have more than one estimator of the population parameter theta,
Then, considering the class of such possible estimators, we can choose the one whose sampling variance is minimum. The graph represents the probability distribution function of two unbiased estimators, one having smaller variance than the other. In the figure, we have two unbiased estimates for population parameter theta, which are theta 1 and theta 2. The variance of theta 2 hat is greater than the variance of theta 1 hat. The one with the least variance, that is, the one which has the least variability or spread, should be preferred. Hence, theta 1 hat is a better measure of the population parameter theta. In other words, an estimator with less variability is said to be more efficient and consequently more reliable than the other.
Now, let us summarize what we have learned in this module. Point estimate selects a single number that is based on sample data that represents a sensible value for the population parameter theta. This value is called the point estimate of the population parameter theta and is represented by theta hat. The representation theta hat does not reveal the statistic used for obtaining the point estimate for theta. Point estimator refers to the statistic used, while its value is the point estimate for the population parameter of interest. The standard error of a point estimate is a measure of the precision of the point estimate. It is the standard deviation of the estimator theta hat and is represented as sigma theta hat. A single population parameter of interest theta can be approximated by more than one reasonable or sensible or plausible point estimator. For instance, the mean could be obtained from the population mean could be obtained from the sample median or from the sample mean or any other measure of central tendency. The use of mean square error to determine the closeness of the point estimator to the true population estimator depends on the value of theta, giving smaller mean square error for some values of theta than other values, since the exact value of theta is not known. The above question can be answered by using only those estimators which have a few desirable properties. These properties are unbiasedness and minimum variance. An estimator is said to be unbiased if the sampling or probability distribution is centered at the true value of the population parameter, that is, the expectation of theta hat is equal to theta in repeated samples. The property of unbiasedness is derived from the general property of the sampling distribution of the estimator and hence not dependent on the population parameter. The principle of minimum variance unbiased estimation directs to choose that estimator among all the estimators of theta that are unbiased, which has the minimum variance. The resulting estimator is called the minimum variance unbiased estimator or MVUE of theta.